LMS algorithm yesterday. We are almost finished it. Then just to recap, it was like this. I mean, input was blocked like this. 0th block was 0, 1 up to L minus 1. This was say 0th block. Dot dot dot. Ith block was from IL. L is the block length. Dot 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 up to IL plus L minus 1. Ith. Okay. Over each block, we are keeping the filter weight constant. Unlike the LMS algorithm, where filter weights are changing at every index, we are doing iteration from block to block. Okay. And within the block, we use the same weight. So basically, the algorithm was like this. I mean, for say I equal to I is the block index, I equal to 0 to 0th block to say final block. Final could be anything of your choice. Final block. Within the block, what are the block indices for the ith block? IL, IL plus 1, IL plus 2, dot dot dot, IL plus L minus 1. So you can introduce the variable R. R will take value 0 to L minus 1. Okay. For R equal to 0 to L minus 1, Y IL plus R. IL plus R means either here or here or here or here or here at these points. Filter, what is the output? Output is W transpose I. It is not IL plus R, because that is constant for the block. That is the difference into the data vector IL plus R. And remember, when R equal to 0, you have data from not only here, but last L minus 1, sorry, last N minus 1, capital N is the block, I mean filter length, N minus data from the previous block. So you have to have those data stored also. Okay, then here also progressively less, but you need to have maximum of N minus 1 data from this, the last N minus 1 data of the previous block stored. Okay. So this is your output. Then IL plus R was your desired response. This is fine. This is one end. Okay. Filtering and error computation you are doing at every index within the block. Once that is done, now you update. Go to the next block. Okay. That starts at Wi plus, yesterday we have seen it is some mu prime by L. Okay, mu prime by L into this entire quantity you can rename as equal to mu, some mu, into there is a summation. So you need more computation actually, there is a summation. The summation was over what? Simply the data vector at each index, IL plus R into corresponding. In the case of LMS, we had only one data vector followed by multiplied by the error. Now it is, you have to do the same thing at all the points and averaging. That is why L factor comes up. And here R equal to 0 to L minus 1. Okay. This is one loop and this is that loop. And initial condition you can say W, the 0th iterate equal to something, W init, which is usually 0 vector. This is the algorithm. You see the algorithm, the problem is weight update computation is now more complex, more computation, isn't it? But all this can be made faster by using FFT, which will be discussed. But before that, let us do a little bit of convergence analysis, just for convergence in mean only, not for that mean square error analysis, which is very lengthy, we know, for this algorithm. And that will be again very much like what we did in the LMS case. That is, suppose we define the error vector, weight error vector for the ith iteration. Earlier it was delta n, now it is delta I. This is only difference, because weights are changing over I, block to block, not over n. So it was Wi minus W opt. W opt remains as usual, that is an optimal filter or inverse P. So from in this equation, from both sides if you subtract, in this weight update equation, from both sides if you subtract delta I, you get, sorry, you subtract W opt, you get delta I plus 1 as delta I plus say mu prime by L into this thing. But I have told you that this error vector itself also contains information about W. So that has to be taken out, isn't it? So this summation remains as it is over R. When I say summation over R, I am not giving the index R equal to 0 to L minus 1, that is understood. But I have given the range of R somewhere, okay. So this first component IL plus R remains as it is, and then this guy is minus W transpose X or X transpose W are same, at least the real case. X transpose IL plus R into WI, but WI is what? W opt plus delta I, isn't it? This together is delta I plus W opt is WI. This plus this, that is what I am doing here. Now apply E over this. So again E over this, and this quantity also E over this. Sorry that I am putting in, I mean for you it could be tedious, but I am using the same equation and inserting an E there just to save time. But you are familiar with these things. This expected weight error vector, I gave it a name last time, I think V or delta. What name I gave? V. So again I gave Vi plus 1 is Vi. This quantity is Vi plus 1. Huh? So this is Vi plus mu prime by L summation over R. See, expected value of this data vector times D is absolutely similar to before. Data vector any index times the desired response, expected value of that is P vector, and P irrespective of the index. So the first term will be P, okay, and then X transpose and W opt. W opt is a constant. So if you take that out, X transpose, expected value of that is R, irrespective of the index. So R as before, R W opt, and you understand this term will cancel, because what is W opt? R inverse P. So this will cancel, this will become equal to 0. So this is one term, this becomes equal to 0. But there is one more term, minus E data vector times is transpose times delta, and here I will be using that independence assumption, that Wi is independent of the data vectors. You see, it is more weird than earlier, because earlier W was independent of the current data vector, but now there are so many data vectors, isn't it, over the entire index, isn't it? Wi actually was obtained from the previous data vectors, for the previous block, but there is a correlation in the data, and not only the data vector here consists of data from the previous block, there is an overlap. So Wi actually, you cannot say strictly that Wi is purely independent of the data vectors present here for all R, but firstly Wi was obtained by the update phenomena by using the data vectors for the previous block, but there is a correlation in the input. So that way, through that correlation, Wi depends on the data vectors or data for the current block itself. Furthermore, when R equal to 0, R equal to 1, R equal to 2, I mean this part of the data vector overlaps with the previous block, and that was used in the evolution of Wi, isn't it? Still we make this assumption, and it works, that Wi is independent of, not just uncorrelated, statistically independent of the data vectors corresponding to the current block. Why statistically independent? Because I told you uncorrelated does not help us much. That is, uncorrelated means what? If there are two variables x and y, Exy equal to Ex into Ey. But if I then come across a situation that E of x square y or E of some fx into gy, I cannot separate out. But if they are statistically independent, if it is giving that probability density of x y is equal to p x into p y, I can then have E of any f x into g y is E of f x into E of g y. That kind of thing will come here, because obviously you see x and x transpose, there are those square terms coming up, isn't it? And then delta I. That is why statistical independence is used. And therefore, what will that give? If I separate out delta because of the statistical independence assumption, delta from this x part, then x transpose will give rise to R at E of delta I. E of delta is Vi. Okay. Now, this is summed L times. Please see, this is summed L times, and L will cancel. So, you get back what we had got earlier. After this, we do not need to proceed. Minus R Vi, which is nothing but I minus R. You remember R was T d T transpose Vi. What did we do after that? We defined in the LMS case, what did we do? We defined T transpose Vi. T is unitary matrix. T transpose Vi. We have forgotten what we did. We pre-multiplied this by T transpose. T transpose Vi plus 1. We gave it a name Ui plus 1. And norm square of U and norm square of V, they are same, because T transpose is unitary. And I was written as T I T transpose. Oh, there is a mu here. Okay, thank you. What is that mu thing? Mu prime. Yes. Thank you very much. Mu prime is a scalar, so T can be moved backward and forth. So I will be written as T transpose, T I T transpose. So you can take the 2T common. Absolutely same equation. Mu prime D into T transpose Vi. T transpose Vi is, there is Vi, which is your Ui. Just a minute. Okay. And then if you take the norm of this vector, that is same as what? T times a diagonal matrix into Ui. You remember that I told you that unitary matrix times a vector does not change the norm. That is why norm of U or norm of V are same. So if I can show that norm of U tending to 0, that means norm of V is tending to 0, and norm of a vector 0 tending to 0 means each component is tending to 0. But what is norm of this or norm square of this? Norm square of this part, because T is unitary, and the norm square of that part you evaluated this diagonal matrix, that will be the first component squared times 1 minus mu prime lambda 0 whole square, the second component square plus 1 minus mu prime lambda 1 square, and dot dot dot. And then we say that if each of these 1 minus mu prime lambda, say lambda k, if it is kept within 1 to minus 1, then this total norm will be less than the norm square of Ui. So this is repetition. From that we derive the condition for mu prime, and that will be same, the equations are same. So for mu prime again we will get the same condition. So in terms of mu, what will it be? So mu prime should be, say, 2 by if you can put this way, trace R, which is less than equal to 2 by lambda max. So in terms of mu it will be, in terms of mu what will be mu, because when you run the algorithm you do not write mu prime by L, you give it a name mu. So that is the step size. So mu will be just L times that, that is mu so this algorithm also convergence in mean. Okay, convergence in mean is established. Now people have done again, a lot of research has gone into LMS. They then try to do the same analysis, that mean square analysis, which we did at length for 3-4 classes. You remember, no? We found out the mean square error in the steady state, that had one extra component called excess mean square error that was evaluated in terms of weight error covariance matrix, K n, rather K prime n. We found out the dynamics of K prime n under some assumption and all that. From that we evaluated that excess mean square and then misadjustment. Same thing can be done here, people have done, but no need to repeat, more or less steps are more or less common. So, we will not go on doing it for all elements, okay, because this just gives you a test. I will do now something which is more DSP, that is its implementation.
So, there should be 1 by L.
1 by L or
So, mu prime by L is
mu prime by, it could be 1 by L or let me see, whether it is 1 by L. See, I wrote quickly. So, this is a very simple thing. Now, mu prime this, yes, mu prime by L, you are right, it will be by L. Thank you. You divide by L, mu prime by L is mu, so divide by L. So, 2 by L tracer, 2 by L, okay. Thank you. These corrections you make. Anyway, since this is video recording, you tell me also. So, it's, officially the correct thing is recorded. If it is a classroom, I would have ignored such comments. Okay. So, now I am interested in the implementation of this. That is why this algorithm is so important, it is very, one full block output and weight update for that block can be carried out for all the indices, filter output, error output and weight update. All these things for the entire block can be carried out much faster than in an LMS algorithm, okay, using FFT and all. So, now we have to get into implementation. Again, I do not know how much FFT or DFT you know. So, again, as is my practice, I start from the basic. You all know discrete time Fourier transform, I suppose. DTFT, all of you know. Please do not ask me to start from DTFT. Given a finite length sequence, Xn, and some of the DSP guys, it is common, I have just taught in your class the other day. Okay. Suppose I have got a finite length sequence. Now, for the time being, forget all this adaptive filter and all. It is pure DSP we are back to. We are using finite length sequence of length capital N. This N has nothing to do with that filter length of capital N. This is a separate topic I am studying. And then I will use this result for the efficient implementation of that block LMS algorithm. Okay. Suppose there is a sequence Xn for N finite length. What is this DTFT? DTFT you know, summation Xn discrete time Fourier transform. All of you know this is a periodic function of omega. You plot it over 2 pi. You either plot it from 0 to 2 pi or minus pi to pi, and this will repeat. All those things you know. This has got magnitude part, phase part, both will repeat because it is periodic. Okay, omega is the digital frequency, its unit is radian. Okay, all that is fine. It is a finite length sequence, this. But for finite length sequence, my claim is you do not need this. See, omega is a continuous variable here from minus pi to pi. But my claim is you do not need the entire envelope. This continuous function from minus pi to pi to have information about Xn. We can live happily by just taking capital N number of samples or more than capital N number of samples. N is the duration of the sequence of these equispace samples from 0 to 2 pi. Could be from minus pi to pi also, but 0 to 2 pi I stick to. That is enough for us. Why? You can very easily see. Actually, this is one shortcut way of teaching DFT, but actual way is, when I will be teaching vector space, then we will see that actually signals can be decomposed and can be written as a linear combinations of basis vectors, a capital N number of basis vectors, and choice of basis vectors gives you DFT or DCT or wavelet transform, Hart transform, Hadamard transform, all those things, But anyway, when I teach vector space, that time again I might just make some remark. But here, quickly, suppose I take the, I sample it, sample at n points, capital N number of points at these frequencies, omega k equal to. So, what is the range? 0 to 2 pi, capital N number of points. So, the gap is 2 pi by capital N. I am sampling in frequency domain, mind you. It is still mathematically it is nothing but sampling operation is done, but in frequency domain, function is a function of omega, but actually sampled. Okay. So, that is why here also aliasing and other things can come up, but I will not go into all that detail. 2 pi by n, this is the basic thing, basic step, times k. K can be 0, 1, dot, dot, dot. So, you understand? 0, then 2 pi by n, then 4 pi by n, 6 pi by n, these are the points I will take the sample. Kth sample will be denoted simply by capital X within bracket k. There is nothing but this guy at omega equal to 2 pi k by n. This is then what? Simply e to the power minus j, replace omega by that formula, this particular discrete frequency, 2 pi into 2 pi by n times k, k times 2 pi by n into small n. Okay. At this specific omega, you are finding out the DTFT, and you are simply calling it xk. Xk is called the kth DFT. DFT means discrete Fourier transform, DFT. So, how many such DFTs are there? DFT coefficients capital N, and my claim is this n samples of DTFT, which I call the n DFT coefficients, they are enough for me to get back xn, and from xn, if I know xn, I can get back these also. So, the envelope can be written in terms of its samples. In time domain sampling also, you know, when you do this sampling and all that, if you follow that non-aliasing condition of Nyquist, then I don't know how much you studied, then the entire function of time, band limited function of time itself can be represented by its discrete samples, by its samples taken at 0, capital T, 2t, 3t, t is the sampling period. So, you do not need the entire information. That is the beginning of DSP, that band limited functions can be represented just by the samples taken at an appropriate rate. Entire f of t can be written as, you know that formula, Nyquist interpolation formula, in terms of sinc functions, sinc and delete, sinc and delete, sinc and delete, sinc. At each sampling point there will be a sinc, sample times this sinc, another sample times this sinc, another sample times this sinc. So, and if you sum them, you will get the entire envelope. So, which means, you know, I mean, you do not need that envelope to be stored. It is enough if you need the, if you have the samples. Okay. Similarly, here also, same mathematically things are same, because when it is mathematics, it does not care whether it is time or frequency, it is variable. It is a function of variable is sampled. So, similar thing will happen here. Here also, my claim is this guy, but here I have not established band limited thing and all those things. Instead of band limited, to be time limited. That is why it is time limited, you see. There it was band limited, this is time limited. I wish I could teach more. If you want to read more, you see my video cassettes available in the net on multi-rate DSP and wavelet or something. Read the, I mean, see the lecture number 1 to 13. That covers most of the basics of DSP. So, these things I dealt with at length there. So, you can see, but this is not a class on that. In fact, I shouldn't have even gone into DFT. I would have simply used background knowledge of DFT, but I know how strong the background knowledge is, so I am starting from DFT. Okay. Anyway, I come back to my claim. My claim is these n samples are enough to get back xn, and therefore this. That is very simple. This is xk equal to this. Suppose an xn duration is capital N. Out of this, suppose I want to find out a particular sample, say mth sample. Okay. What I will simply do, you know, this is common in all Fourier transform, analog Fourier transform, inverse transform, DTFT, inverse DTFT. If you want to find out a particular thing, say x small m, you multiply both sides by e to the power plus j 2 pi k by n into small m. And sum over k. K again, how many? Capital N. Here also you will have double summation then. You multiply this by e to the power j 2 pi k m by n, and then sum over k. Double summation I will interchange, there is a very obvious step always. X n is dependent on n only, so it comes here, k here, and e to the power minus this is already there, and e to the power plus the same thing with m. So, you can say j 2 pi k by n. Okay. Look at this summation. M is your choice, small m is your choice, right? Now, n is varying. For each n, you are running the summation. For each n fixed from outside. So, when n becomes equal to m here, m, because n will become m, because m is taken from this range only. When n hits m, that time it is 0, e to the power 0, 1, 1, 1, 1, 1, 1 added n times x m. So, one term is n times x m when small n equal to m. And now consider the situation where small n takes other values other than m. That times this is an integer, positive or negative, I do not care. And then this is a GP series in k. If you say a equal to e to the power j 2 pi by n into m minus n, and m minus n is non-zero now. If you call it a, simply it is a to the power k. So, 1 minus summation will give rise to what? 1 minus a to the power n by 1 minus a. This summation, a to the power n means n cancels, e to the power j 2 pi into integer is 1, 1 minus 1 0. Okay. So, that will be giving rise to 0. So, you will get back this, which means x m is nothing but 1 by n times this. So, you can get back any sample. Actually, the reason why it becomes 0 is like in the case of continuous signals, if you have a cosine or sinusoidal signal and you integrate it over a integral number of period, it is 0. Here also for this choice of this 2 pi k time by n, this kind of choice of omega, or 2 pi into some integer by n, k if you go on adding, you are basically you will be completing one or more than one period exactly, and that is why it becomes 0. It is not for any small omega here. Do you know this, that sine analog frequency I denote by capital omega, sine capital omega t or cos capital omega t is always periodic. Period is 2 pi by capital omega. But sine small omega n is not periodic in general. Do you know? Sine omega n is not always periodic. Because for that we see, I am again getting diverted. Sine omega n, omega is radian here. Earlier I said sine capital omega t, radian per second analog. This is always periodic. But here it is not in general periodic. If it is to be periodic, then period suppose equal to capital N. So, that must be some capital N, so that this. So, omega into capital N should be either 2 pi or 4 pi or 6 pi something. So, only for those kind of choices. Huh? No, it is their problem. Now it's coming. They are looking here and there. They are not.
N cannot be a multiple.
So, capital N is an integer. So, omega into capital N has to be your 2 pi or 4 pi or 6 pi or something, isn't it? Integral multiple of 2 pi. So, 2 pi into k. Omega n should be 2 pi k. That is why omega should be 2 pi k by n, and that is what is coming here. What is that? You understand that? Is it? Okay. So, that is why this periodic thing comes up, and that is I made the statement that you will really integrate a full number of periods for this kind of choice. But mathematically you can see it is 0. So, that means instead of small m now I write the general form for any x n, any sequence x n is 1 by n this is called inverse DFT formula. From the DFT coefficients how to get back x n. But remember you can treat this formula, and that is how it should always be taught, as what? For each k, this is the signal, I call it a carrier or a basis function. For each k here, this is a sequence, n takes various values, it is a sequence from 0 to n minus 1. K equal to 0, you can view as though it is a DC, k equal to 1 first harmonic, k equal to 2 second harmonic, k equal to 1 fundamental, k equal to 2 first harmonic, like that. Okay. So, various sequences, they are multiplied by some coefficients and added. So, it is a linear combination of some basic sequences. One sequence is for k equal to 0, another for k equal to 1, like that. So, it is basically combination of some basic sequences. Their linear combination gives any x n. Only the coefficients carry the information about x n. This is the vector space treatment, which we will study later. that any xn can be written as a linear combination of some basis sequences. Basis sequences have to be basis sequences. They should study. In fact, they are orthogonal sequences. All those things we will study later. Okay, I will come back to. I mean, when I teach all that in a context of orthogonal projection and all for estimation problems, I will again take this example. That look, I did this that time. This is what happens. Okay, this is IDFT. This is your DFT. This is IDFT. Fine. So I proved my claim that from the samples of the DTFT I can get back xn, and from xn putting back this xn here I can get back capital X e to the power j omega. So DTFT itself can be written by its own samples. DTFT samples are good enough to write the express the DTFT mathematically. Okay. Now look at this, that suppose I have got a sequence, finite length sequence. Here n, this is from and this is h n, this is say y n. X n and h n are finite length. For the time being, suppose you assume that both are same length. If not, you can add some zeros and make them say same length. Length is say n. That is here n is less than equal to, that is x n, or if you want you can do like this, x n is for n equal to, in the most general case, say capital N minus 1 0 h n not n m, this is m, huh? Length n, length m. Okay, for the time being I come back, we make them equal to n, that will be easier for explanation. So both are length n. Now you know one thing, y e to the power j omega, this DTFT, please see, is x e to the power j omega into h e to the power j omega. That I think all of you know. This much DSP was covered. So okay, this product you know, that is equal to this. Therefore, if I take sample this and if I sample this, I know if I sample this function, its length is capital N, length is capital N. So if I take n samples here, n samples here, those samples are good enough for this. So suppose I take this product only. So its k means nothing but DTFT at a particular frequency. DTFT at a particular frequency. These two if you may multiply, you should get back this at the same frequency, isn't it? 2 pi k by n, and k is 0 1 dot 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 n minus 1. Question is, if you call them, say for the time being, some instead of y k I am writing y prime k. If I use them in the inverse DTFT relation, from these samples, inverse DTFT, do I get back y n? Answer is no. Why? Yeah, he understood. Yn, length of Yn is what? Not n. 2n minus 1. So firstly, its DTFT should be sampled at least 2n minus 1 times, and there the basis function should have been e to the power j 2 pi k by 2n minus 1, not n, times n, multiplied by the corresponding coefficients, yk or whatever you say, and k will go from 0 to 2n minus 2, total is 2n minus 1, then it is okay. But I am not having that. I am having only n number of samples, and like a fool I am just running the IDFT as though the sequence length was capital N. So summation will be from 0 to n, n minus 1, this thing. Same 2 pi k by n only here, not 2n minus 1, 0 to n minus 1 only, not 2n minus 2. So obviously I will not get back the correct yn. You understood this problem? I said that fine, I won't get. Then what do I get? You can evaluate that what do I get. What I get will not be yn. Yn is obtained by linear convolution between x and h. You all know linear convolution, graphical way of doing it. Please don't ask me to do that. What yn will have? We will have not only the linear convolution, there will be another component which is the error component. We will see. Together will be the total yn. this yn, the way it is generated, that is 2 DFT multiplied and taking inverse DFT, it is called circular convolution or periodic convolution, which will have a component of linear convolution plus an erroneous component. I have to then do some manipulations to throw away that, to remove that component, that to make sure that extra component is 0. Okay. But before that, let us then evaluate what really we get. If we still stick to the range 0 to n minus 1 only, what do we get? Okay. So suppose I call them y prime k, that is why I am not calling them yk. If it is strictly yk, I should take 2n minus 1 points of samples of its DTFT and all, that I am not. I am simply calling the product y prime k, and like a fool I am putting them in the IDFT formula, hoping that I will get back yn, which I will not. So what I will get back is not yn, so let me call it y prime n, and I will see how much difference is there in y prime n from yn. I told you linear convolution plus an extra component will be there in y prime n. Okay. So what is y prime n is 1 by n, that IDFT formula, but with these coefficients. Range is as before, not 2n minus 2, but n minus 1 only. Okay, times e to the power j 2 pi k by n into small n, IDFT. Okay. And now y prime k you replace by this xk hk, and xk hk, because I want to finally relate everything in time domain, isn't it? Linear, how it is related to the actual linear convolution. Linear convolution is time domain. If I put y prime k equal to xk hk, still on the left hand side I have got n, right hand side xk hk, not a small xn, not hn. So again xk has to be written by its DFT expression involving xn, hk is to be replaced by its DFT expression involving hn. I will get a triple summation kind of thing. So that will at least relate y prime sequence with small xn, small hn, and that I will simplify, and I will see that okay, there will be some component which is coming from the linear convolution between the two and an extra component. Okay. So y prime k is, next step is you replace by these two. Simply that is put this equal to xk into hk, and next step will be replace xk by its formula of DFT, hk by its formula. What is the formula? The DFT sample, DTFT sample. Okay. I might go fast here actually, because by now you should be familiar with what I am doing. This is x, do not use n here, n is fixed by your choice, xk, so use xl, e to the power minus j 2 pi k, k is your k is fixed from outside summation, kl by n, l from 0 to n minus 1, this is your xk. We are sampling the DTFT of x. Similarly here hk, same thing, but use another index hm. Okay. So xk, hk, and this other term e to the power j 2 pi k n by n. Now three summations, we have to interchange the summations. This k summation, push it absolutely inside, let it be innermost. Let this be over x, summation over L, so only XL remains here. This involves K. This term involves not only L but K. If I have an inner summation over K, so this will go there because it has K, this has K. This exponential all will be inside because the innermost summation is over K. Are you following this? This outermost becomes innermost. Whichever has K, that those are pushed in. This has K, this has K, this has K. Okay. Fine. Firstly, all of you have seen earlier that whenever this argument n minus m minus l is non-zero, then this is a GP series because series is in terms of k. You call the entire thing a to the power k, so that will be 0. So this will have value only when m and l, they are taking various values. Now they are taking values so that either m plus n equal to n or n plus capital N or n plus capital 2n 2 capital N and all that. Then this will become equal to 1, it is equal to 0, 1, and 1, 1, 1, 1 n times, that n will come, this n will cancel, and you have got these things, some term of x, some term of h, depending on the particular L and M we had at that time, the product of 1x, 1h, fine, isn't it? Otherwise 0. So that means in this summation what you have to do, only when L plus M is equal to n plus R into n, R can be anything, R can be 0, plus minus 1, plus minus 2, you understand? N or n plus capital N or n minus capital N, you put back here, the entire thing will be e to the power either 0 or e to the power 2 pi, j2 pi, integral multiple of 2 pi and all that, okay, you will get 1. Only then this will be non-zero, 1, 1, 1, 1 n times, n will cancel, x of particular L and particular h of particular M as coming from this, they will be multiplied. Okay. So now let us see what happens then. Please see that books do not discuss this in this detail, they just work out a formula, but this will tell you how to handle DSP. Let us draw two axes. This is for L 0 to n minus 1, this is for M. L is also varying from 0 to n minus 1, so does M. Suppose L is 0, then M is varying 0, 1, 2, 3, only when M equal to, in this range, small n, because small n you are speaking from the range 0 to capital N minus 1 only. So, when only when M hits small n, this is satisfied, or when M hits n plus capital N, but can small m be n plus capital N? Answer is no, because all the indices have got limited range 0 to n minus 1. Small n plus capital N means you are jumping beyond the range, so that will not occur. So, only when, so for L equal to 0, small m equal to n, that is enough. Okay. So, x 0 into h n, then again this will be satisfied, you will let 1, 1, 1, 1, 1 added n times, n cancels. So, one term will be, that is, suppose this is n, this with this, one term will be x 0 into, sorry, x 0 into h n, then L takes 1, L takes 1, the moment L takes 1, M should be what? N minus 1, so that this is satisfied. L is 1, n minus 1, you understand, this is increasing, this should decrease, so that summation is small n. M is n minus 1 or n minus 1 plus capital N, but that will go again beyond the range. So, only n minus 1 is fine. Dot 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 dot, L is increasing, when L touches small n, that is x n, M should be 0, 0 plus n still n, 0, or if you jump again 0 plus capital N, you are beyond this, okay, not allowed. So, x n into a 0, other terms, but look at this, what is this? What is this expression? Linear convolution between x and h evaluated at nth index, but I will again come to this. Let us come to this further. Now, L is increasing, n plus 1. So, n plus 1 means it should be, M should be 0 minus 1, then minus 1 and 1 cancels, it will become a small n, but minus 1 is again beyond the range. So, what do I do? From there, if I jump to the right by capital N, I hit back a valid point, capital N minus 1, isn't it? So, that means h n plus 1 into x, h or x, sorry, this is x, this is h, x n, x n plus 1, h n minus 1, and n, as you go on increasing, if it is n plus 2, this will be capital N minus 2, so on and so forth. Easiest way to remember is if you add the two indices, they should amount to small n plus capital N here. Here if you add the indices, it should amount to small n. This is this extra component that is coming. This is the extra component that is coming up. What is this component? Those who cannot see that is circular linear convolution, look at two sequences xn and hn. Okay. Say h, when you convolve, you know the formula, na? You know how to convolve, no? Graphically, all of you know this. Say h r x n minus r is r minus n summation over the available range. So, before r minus n you are given say x of n, so reverse it, say x of r, reverse it, so it becomes x of minus r. Instead of r replaced by r minus n, that is shifted by n, if n is positive shift it to the right by n, and then multiply the two, so sample wise add. This is a convolution, and suppose it is h0 h1 dot 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 h n dot 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 h n minus 1, fine. X also was a sequence like this from here to here. First you reverse it because it is minus, and then shift it by small n. If you reverse it, x0 x1 x2 dot 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 on this side, and then you shift it to the right by small n. So, x0 comes below this, x1 comes here, just shift it, dot 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 x n comes here. If it is n, it is 0. So, if it is 0, it is n, and if you multiply, then other terms here get multiplied by 0, 0 multiply this term. So, forget them, only this part you multiply, you get back x0 h n. You understand, na? These are linear convolution, but that is what I wanted, but I am getting the extra term. This together is called circular convolution. But before I can eliminate this term by some trick and all that, I should have a graphical way of interpreting this, and that graphical way of carrying this computation, graphical way, like this is a graphical way of linear convolution. So, graphical way of doing the entire thing, I will now present, then you can verify. Just follow the procedure that I suggest. That suppose you are giving two equations, two sequences x and h. So, you are given two sequences, say h or and also x. Okay. Shall I just dictate or shall I write? Before you do the circular convolution, what is circular convolution? Actually, you are doing endpoint DFT multiplying inverse DFT. You will get an endpoint sequence. What is that? That is not linear convolution, it is a kind of complicated thing which you evaluated. How to get that graphically, that is what you are saying. So, that is called, that sequence is called the circular convolution output between, or periodic convolution output, that is obtained by periodic convolution between the two, or circular convolution between the two. Now, first step is hold one sequence as it is, do not change h, say. Next step is make a periodic version of this, that is construct a sequence by repeating this again to the right and to the left. Okay, I am not doing all those, Third is reverse. Third is reverse this. That is, unlike linear convolution where you just reverse this, here do not reverse this, the given one, make a periodic version, then reverse. After reversing, again the same step, shift it to the right by small n. These two are common, reverse and shift, these two are common. But after that, when you shift to the right by n, still this is an infinitely long sequence. Now you use a chopper, that is, or window, that is to the right of capital N minus 1, whatever you have in that shifted periodic sequence, throw away 0, to the left of origin throw away 0, again you got a finite length sequence of length n. Now multiply sample wise from h, sum, you should get that. That is my claim. and that you can verify. I don't know how much time you have today. Suppose you do this, you make a, I mean, I am not showing the intermediate steps. Suppose you make periodic repetition of this, reverse it, and now you will go on shifting. Okay, you will go on shifting. So today there is no time. I would suggest that you take it up on your own. Okay, and next time we have to consider, because once I start it, it will take about 10 minutes or so. This graphical business, but that is very important. Once that is done, then some property of this we will see, of the circular convolution, and that will be using in the filtering part of that block adaptive filter. Then again we come back to the DFT, some property of circular shift, not ordinary shift, circular shift. We will have to see that effect will be used in the computation of the weight update. Okay, that weight update part, you remember there is a summation of some data vector times errors. It's actually some kind of correlation. So using DFT, what will be using, circular correlation property of DFT, and circular convolution will be in the filtering part, convolution, linear convolution. I will use circular convolution cleverly to get linear convolution result. Similarly, I will use DFT and the circular correlation property to use to get that correlation. And this DFT, you remember why, I mean, maybe just 2-3 minutes. Why you are bothered about DFT? Because there are very fast algorithms available. Like, I mean, if you see this simply DFT computation, xk for each k, how many complex multiplications? Capital N, isn't it? N samples are complex multiplications and n minus 1 addition. Each complex multiplication means how many actual multiplication? 4, a plus jb into c plus jd, 4. But cleverly we can reduce it to 3. That I will tell you some other day. People have found out way of adding some term and subtracting some term, and it can be reduced to 3. Some 2 adders will go up, but even then that is quite huge. So if I assume order, I mean n multiplier, and how many k? Nk. So order n square. And suppose you are having a sequence of length 512. So you understand how much computation 512 square. But there are fast algorithms where, so if n, length n is a power of 2, say 2 to the power r, then it should have r into n, or equivalently order of n log 2n. This can be reduced. So you understand 512 means 512 square, and here it becomes 512 into 2 to the power 8, so 8. You can brought down to that level. That makes it very fast. Unfortunately, I cannot teach this here, this FFT and all that, but that is the reason why you will go for this. And there are plenty of excellent architectures available to implement it. There is a motivation for going into DFT. So I stop here today. Please come with some preparation of this, so that the recapitulation time is less. Okay? Okay, thank you very much.